Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be completing Chapter 16 on discriminant analysis with the too often used Fisher's iris data. So Ron Fisher, who is an amazing statistician, he basically developed experimental design, ANOVA, and many of the tests that we use every day. And for as great a statistician as he was, I understand he was an even better biologist, and which was his primary field. And he has a famous data set called the iris data, which consists of 150 flowers, 50 flowers each of 3 different species, Setosa, versicolor, and virginica. And measurements of 50 flowers of each type were taken in millimeters of the sepal length, sepal width, and the petal length and petal width. And I have an image here of an iris and what the petals and sepals are. The petals are the 3 petals with the purple coloring, and the sepals also look like petals, but they're sort of the second layer, and they're not petals. They're sepals. So if we measure the length and width of the petals and the sepals of each flower, let's see whether we can use discriminant analysis to tell these 3 groups apart. So I'll read the iris data set in. It's actually built right into R, so I don't need to read it from a data file. And I'm going to plot the data, and here's a big scatter plot of the iris data. We've got the 3 species in colors. The red is the Setosa, the green is the versicolor, and the blue is virginica. And you can see some striking differences, particularly look at the petal length and the petal width. The petals for Setosa are quite a bit smaller than for versicolor, and virginica has the largest petals. In terms of, and if we look at the box plots above, you can see how much just the petals, even one petal measurement on itself, can pretty well distinguish these 3 species of, or varieties of iris. For sepals, there's also some discriminant power, but it's not as strong, right? There's clearly some difference there. Again, Setosa tends to have the smaller sepal lengths, but also slightly wider sepals than the other 2. So our question is, can we find a couple canonical discriminant functions to best classify or separate these 3 varieties? I'm going to show you a parallel coordinate plot. Let's see, is there a package for this? I think this is right in galley. And I'm going to show you 2 types, and then we'll discuss the benefits of each. So what a parallel coordinate plot is, it's a strategy for plotting multivariate data where along the horizontal axis you have each individual variable. And then on the vertical axis you have a value of that variable, which may be scaled. So on the left, each variable, such as petal length or petal width, has been scaled to fit between 0 and 1. So it's basically taken the minimum observed value and mapped that to 0, the maximum observed value and mapped that to 1, and then everything else falls in between. And one pattern we see here is Setosa starts low for petal length and width, and then it actually becomes greater for sepal width, whereas the opposite pattern basically follows for versicolor and virginica. On the right, I've used global min-max scaling so that over all 4 features, petal length, width, length, sepal length and width, something close to 0 is the minimum value, something close to 8 in this case is the maximum value, and everything else is sort of scaled. So this helps preserve the relative scaling between the individual variables. So we can see that lengths are all greater than widths. You can see all those negative slopes, and for both petals and for sepals. And in fact, sepals tend to be longer than petals because of the relative heights. And you can see how observations within a group, such as setosas, all move together. So the code up here is just GG parallel coordinate, and the main variables or options to think about here are scale is and choosing uni min max or global min max, and selecting which columns in the data set that you're plotting and which column in the data set defines what your groups are. I've also added the box plot equals true, which put box plots for all the observations together behind the individual lines. So how many canonical discriminant functions are there? Let me scroll up for a moment and remind us how many there can be. There can be the minimum of P, which is the number of features, and K, which is the number of groups. So here we've got 4 features. We have the length and width on petals and sepals, and we have 3 groups. So the minimum of 4 and 3 minus 1, which is 2, is 2. So we should be getting 2 canonical functions. And so that's what this says here. We should be getting 2. So recall, we first start off by fitting the linear model object by column binding all the response variables together versus the species. That creates the linear model object, which I'm calling lm.iris. Then I'm putting that into the canonical discriminant function, and we'll start off by looking at the coefficients. And you can see that we've got 2 canonical functions, just as we predicted. And these are the loadings for those 2 directions. In the first direction, which is the single direction that best discriminates the 3 species, it's a contrast between the sepals are both negative and then the petals are both positive. So it's basically a contrast between the size of the sepals and the size of the petals. The second function is a little less easily interpreted. This first sepal length is basically 0, so we're going to ignore it for our interpretation. We have sepal width is positive and petal width is positive. So it seems that the widths are one direction, and then the petal length is negative. So this is sort of a contrast between the petal length and the widths of the petals and sepals, with the sepal length not really being an important part of that. So let's plot the data using the scores of the canonical iris object. The scores are going to be the coordinates of the observations on the canonical axes. So I'll zoom out a little bit. So maybe we'll start by looking at let's start looking at canonical direction 1. So here, this middle column is canonical direction 1, and take a look at these box plots and how distinct these 3 groups are. Setosa is miles away from either versicolor and virginica, and even those 2 barely overlap on their whiskers. So we get almost perfect separation on using 1 dimension rather than the original 4 dimensions that we had. If you look at the that same information but in histogram form, you can see just the narrow overlap here. On the second canonical direction, this is the rest of the information in terms of explaining the differences. And this second direction is perhaps helps a little bit to distinguish versicolor from the other two, in particular Virginica, since there's a little bit of overlap here with Virginica. But you can see that canonical direction 2 does not provide a lot of information for separation. If we look at the scatterplot matrix, and I'm going to focus in on that, we've gone from 4 dimensions to 2, and you can see how you could draw basically a line through here and distinguish setosa from the other two. And then you can imagine another line, basically maybe at a slight angle through here, which best separates versicolor from Virginica. Just looking at the canonical discriminant object can.iris, when we look at the canonical discriminant analysis for species, direction 1 accounts for 99.1% of the discrimination ability between the 3 species. Yes, that's basically everything. A little bit less than 1% separation comes from the second direction. Though there are, in both directions, significant differences between the 3 groups in terms of something like a multivariate, or this would be a univariate ANOVA test along each of those separate axes. So there are some assumptions for the canonical discriminant analysis, in particular equal population covariance matrices across species, as well as multivariate normality. So if we take a scroll up and look at the scatterplot matrices, the bivariate scatterplot matrices, do these appear the same for the 3 groups? Well, in terms of multivariate normality, these are particularly the green one perhaps, are each fairly elliptical. So that's not too bad. We have sort of 1 or 2 outliers occasionally, which is not perhaps that unusual in a sample size of 50. But one observation is that the covariances probably are not equal. Setosa has this negative slope, so the correlation here between these 2 canonical directions would be negative, but the blue here seems to be positive, and same thing with green. Oops, sorry about that. I think the original assumptions are on the original features, however. If I page way up to these scatter plots, in particular maybe the difference, the bivariate scatter plot for petal length and petal width, you can see setosa is this tight ball, whereas the other 2, versicolor and Virginica, are a bit more spread. So it looks like perhaps equal covariance matrices may not hold for this data. We'll see in the next chapter something called quadratic linear discrimination, which allows for unequal covariance matrices. So here are the 3 covariance matrices by each species for the 4 features in the iris data. And maybe one place to start here is the diagonal matrix. How about the individual variances for sepal length, sepal width, petal length, and petal width? To me, this looks like the setosa values are maybe about half of what they are for versicolor, and maybe about a third of what they are for Virginica on sort of a rough eyeballing of it. Some of them don't have that quite as drastic values, but some of them are quite drastic. Here's 0.03, and here's 0.3. So there's some differences there for sure, and if you inspect the off diagonals, there's going to be differences there as well. If we ask about multivariate normality and perform the multivariate Shapiro normality test for each of the three species or varieties of iris, we see Setosa does not, has 0.08, versicolor 0.005, and Virginica 0.008 for their p-values. So there's some evidence there that the three groups are not multivariate normal, and if we use this function for plotting basically a QQ plot for multivariate normality, we can see some deviations from that diagonal line. And perhaps they all sort of deviate a bit. So in the next chapter, chapter 17, we'll be looking more closely at classification. So how can we use these canonical directions to actually find rules for classifying groups?